We will create a simple neural network in order for you to understand what exactly loss.backward does and how it integrates with optimizer and the neural network and how the neural networks learn. This is probably the most important line of code in PyTorch. It's loss.backward. Usually you will see it like this: loss.backward, optimizer.step, and optimizer.zeroGrad. So loss.backward is gonna trigger this engine, Autograd, that is used for neural networks to learn. This is how neural networks learn, using Autograd, using differentiation or gradients. If you want, you can watch my course to become AI researcher from scratch, or you can watch neural networks or math. So neural networks and math and PyTorch are actually all included in this course. But if you don't want, if you have some basic understanding of neural networks and math, then you don't need to watch it. So let's say we have some input to the neural network X. Let's set it to be just one single value. And our target, what we're trying to teach the neural network to predict, let's set that as 2. So now neural networks is gonna have some, it's gonna multiply this input with some weight and add some bias. So it's gonna be X input plus some weight times some weight plus some bias, and it should give this output too. So what should be weight and bias? So the neural network needs to learn what should be weight and bias, which number should be here, to go from 1 to get output 2. Let's say at first we set weight at 1 and bias at 0. So we're gonna do the following. We're gonna do input times weight plus bias. So it's gonna be 1 times 1 here, 1 times 1, those are our values, plus 0, so the prediction will be 1. And so if we say prediction, which is our 1, minus the real target 2, that's gonna be minus 1. And then we square that to get 1. So the reason we are squaring this loss, this difference of our predicted and the actual, so first of all, know that this is gonna be the error. But we wanna square the error for 2 reasons. First of all, we wanna make it positive. It's gonna be easier to work with. Secondly, the bigger the error here, squaring will make it a lot bigger. You know, squaring a large number makes the number way larger. So it's like we are punishing the model even more for getting a bigger error. So this loss works well in practice. So I'm gonna run all of this code on Google Colab, what I just explained earlier in the beginning. And the loss is gonna be 1, as I explained. So we can check gradients before loss.backward. So there is no gradients in the weights and bias. So I explained what gradients are in my course that I mentioned earlier, AI Researcher, but gradients is gonna show you if you change weight numbers. So if you increase, is the loss gonna increase or decrease? If you change bias, increase or decrease, is the loss gonna increase or decrease? So gradients will show you how to change weights and biases so this loss, this error goes down. If the error goes down, it means our neural networks is predicting better, it's working better. So again, we need gradients to figure out how to change these weights and bias numbers, increase or decrease, to make the error go down. Then I'm just gonna call loss.backward, and what this will do is calculate gradients, gradients of loss with respect to weights and gradient of loss with respect to bias, or biases if there is multiple. First, let's see now the gradient. So gradient of W is -2 and gradient with respect to B is -1. This means if you increase W by a little bit, the loss will increase by 2 times that. So this negative sign of W gradient being -2 tells you that if you increase W, the loss will decrease. And it will decrease So 2 is the magnitude, so it will decrease by 2 times of whatever the increase in W was. But there is a catch. The gradient is only valid for that point at W, and maybe a little bit around it is approximately that gradient of -2. Because let's say you are standing somewhere on this surface, it will tell you if you move in this direction, it will decrease the loss by -2 times. But remember that as soon as you move in that direction, now the slope will be different, the surface will be different. So by moving, you change the gradient itself, so it will no longer be -2. So keep in mind that. So we can say here that if you increase W by a little bit, then the loss will decrease by 2 times of that little bit. But if you increase W by a lot, then the gradient itself will also change. It will be a different point on the surface, so we don't know what's going to happen. That's why we have a very small learning rate. So when we are updating actual weights, we're going to multiply these gradients with 0.001 or something. It's a very small learning rate because we want to just move a little bit. We don't want to move too much and change gradient too much, because we don't know what's going to happen if we move too much. But now let's go back to this loss.backward. Let's see what it actually does. So we know that first we calculated loss, which is going to be our weights times input plus bias minus the actual true value and squared. So this is our neural network and loss. And then we would take a derivative of this loss function with respect to W first to see if we change W, how does this loss change. So that's the derivative, or I should say partial derivative, because we will also take partial derivative with respect to B later to see if we change B, how does the loss change. So this is the partial derivative or derivative with respect to W. And so that's going to be our part of our gradient. So it's going to be this -2. If you want, you can watch my video backpropagation from scratch on my channel. So it's going to explain like derivation and math behind it more. So after you calculate loss.backward, you would do optimizer.step. So this would update weights using this gradient. As I said, the gradient of -2 is huge. It's a huge step. So we will multiply it with learning rate. Depending on the optimizer, is it Adam, is it a muon? Learning rate will be maybe 0.001 or 0.01 for muon. And so we will just subtract from the weight, we will subtract this. So when we subtract this, then loss will decrease, because if we added it, loss would increase, because this gradient actually shows you how to go up the function, up the loss. So we want to go down the function, so we will subtract. And so that's what this optimizer step will do, but there is a catch. You need to always do optimizer 0 grad to remove the value of this w.grad, because if you don't do that, then it will just add or sum up all of the gradients for every iteration from past data, which is a bug, which would be bug in your case. It's not a bug depending on what you're doing with it. So why does PyTorch not automatically zero out gradients? This is useful for recurrent neural networks, or when you want to split a large batch of data into smaller mini batches to save RAM, summing their gradients before updating weights. Anyways, let's see full example of the training. It's very simple neural network, starting with x1, y2, the prediction, okay, and then initializing weight at 0 and bias, weight at 1 and bias at 0. We initialize this because we're going to be multiplying with weight. So in the beginning, multiplying with 1 will not change anything. Adding 0 will not change anything. That's one way to initialize these parameters, but there are different ways as well. And we want to say require grad true because we wanted to track gradient so we can update and optimize. We will just use stochastic gradient descent. This is the simple one. Learning rate is pretty high here, which works in this case. And I'm gonna print where it starts from. So starts from these two values. Loss is gonna be 1, as we calculated. And then each epoch, we're gonna try to make the loss go down. So the difference between the predicted and the correct value, we want it to be smaller and smaller. So the error should be smaller and smaller. And we can see here that I wasn't even printing loss, but now I added it. And so loss starts at 1 and then goes down, down. So I guess if we increase number of epochs to 30, let's see. Loss is going down, so loss now is absolutely 0. And if I also print bias, let's see how bias changes. So bias starts from 0, but then it keeps getting updated, and then they settle at weight 1.5 and bias 0.5. So 1.5 times 1 is 1.5, plus 0.5 is 2. So this is gonna give us the exact number 2. It's gonna convert our input 1 to 2 exactly. That's gonna be it for this video, and see you in the next one.